Good morning, everyone. Welcome back. So, this is lecture 20, and we are going to continue with what we had left. So, it has been, of course, long time, and I hope you guys are doing well at your places. So, we were doing work energy principle, which we will continue with some examples. Okay. So, you can recall that in the last class, we were doing this example where we had this mechanism. So we have a vertical fixed rod and there's a collar which can move up and down, and there are two rods attached to this collar, and these slanted rods are further attached to disc, right? You can recall it. Okay, and there's also a spring here. This collar is frictionless, okay, which means as this collar moves up and down, a constant friction F is acting. Okay, so that's given. Constant friction F acts on the collar from the vertical rod. The collar has got mass, let's say M3. The links, the slanted links, suppose their masses are M2 and length L, and finally the discs. Okay, so they have masses M3 and radius big R. Alright, so this is a very interesting work energy question. So what's happening here, let's say the setup is left from rest when this angle is theta. Okay, and we want to know what's the velocity of each of the discs, the links, and the collar when this theta is something else. Okay, so initially it is theta 1, but at an arbitrary theta, as it goes down, what is the velocity of each of those components? All right. The interesting thing here is that the velocity of collar, for example, will define the velocity of the two links as well as the disk. See, it's given that the disk is undergoing rolling without slip. So there is sufficient friction between disk and the ground. So if we say that the velocity of the collar is v, then the angular velocity of the link and the translational as well as angular velocity of the disk, they are all completely set just by the velocity of the collar. So it's in a sense a single degree of freedom system. So just the velocity of the collar is the only unknown for which perhaps you need just one equation, right? One unknown, so one equation should be sufficient. And that equation is the work energy equation that we have seen till now. So let me remind you that equation. So it's W dot by the conservative forces plus W dot by the non-conservative forces. That's equal to K dot, right? So work done by conservative and non-conservative forces. The rate of work done on a system is equal to rate of change of kinetic energy of that system, isn't it? So here we can treat the collar, the link and the disk together as one system, and everything else is then external, right? So what is external to the system here? So if we say that two disks, two links and collar, these are our system. This constitutes the system. Then this spring is then external to the system. Okay? And now let's think of applying this work energy principle. So you see the internal forces. So you have a system and internal forces of a system does no work, isn't it? Can you recall, for example, when we were looking at the disk, then we also had the link. The link applied reaction forces on the disk, and disk applied the reaction force on the link. But these action reaction forces or the internal pair forces together does no work. The work done by the action on the disk exactly cancels the work done by the reaction on the link, right? So work done by action on the disk is exactly cancelled by work done by reaction on the link, isn't it? You see, for example, what are the action reaction pairs? Let's identify. So these two, they are action reaction pairs, and likewise these two, they are your action reaction pairs. And why the work is cancelled? Because the point of application of the action and reaction, that point is undergoing the same displacement, isn't it? See, what's the action, what's the point of application? So for the disk, if it is O, then here we have, let's say, B. So O and B, because they are pinned together, so they undergo the same displacement. And because action and reaction are opposite to each other, so force times displacement and reaction force times displacement, when summed together, becomes 0. But there could be a situation when the action and reaction are acting on the point of application which does not undergo the same displacement. In that case, the work done by action reaction pairs will not be 0. Okay? See, for example, we have this, we can see this here also. Look at this collar. And the vertical bar. If we also take the bar as part of our system, then the friction force between the collar and the bar, that's internal, isn't it? So the bar exerts friction force on the collar and the collar exerts the reaction friction force on the bar. So they are action reaction pairs, but does it do any work? So work done by the action, that is by the bar on the collar, that friction, it's acting on the point of the collar, right? And from the collar on the bar, it's acting on a point on the bar, but a point of the bar is not undergoing any displacement. And you can see there is a relative motion between the collar and the bar. So the point of application of the action and the reaction, they are not undergoing the same displacement. Therefore, the work done by friction force here is not zero. Okay, so I can make that remark also here. If the point of application of action and reaction pairs do not undergo same displacement, then the net work done is not zero. Okay? But if they undergo the same displacement, then of course it is zero. Anyway, so again, our system is now the collar, the link, and the disk. And we want to apply work energy principle to this system. And fortunately, all the internal forces for this system, they do no work. So while applying the work energy principle, we only have to consider the external forces to the system. The work done by the external forces to the system only needs to be considered. Okay? So, and you can recall that this equation right here was also written in a different form. The work done by conservative forces can also be written in terms of potential, isn't it? But negative of the potential, isn't it? So this is minus Vc dot plus W dot Nc is equal to K dot, which could also be written as W dot Nc is equal to K plus Vc whole dot. Okay, where Vc is the potential of only the conservative forces. So this is the rate form, and then you also have the integrated form, in which case we simply have Wnc is equal to K plus Vc 2 minus K plus Vc 1. So work done by a non-conjugative force in going from state 1 to state 2, that's simply the total energy at state 2 minus the total energy at state 1. Alright? Okay, so let's come back to this problem. So what is our goal here? So we want to find out the velocities and the angular velocities of each of the components of this system when we have an arbitrary theta. And we may also be interested, for example, in finding out, let's say, what is the acceleration of the collar at the instant when it is just left from this position. So at theta equal to theta 1, we were holding it and we leave it. Then due to gravity, the collar is going to go down and there is friction acting. So at that instant, what is the acceleration of the collar? Okay, so how to find these things? So maybe let's first try to write down the kinetic energy of the system and also the potential energy of the system, and then we can apply the work energy theorem. Okay, so for the kinetic energy, you see we need the velocity of the collar which is prescribed, and we want to find out everything else in terms of the velocity of the collar. So let's see how we can find it. So I'm again going to just draw the collar, then we have the link, and finally we have the disk. The collar, and let's also have the coordinate system. This is I, this is J. Suppose that the collar is going down with a velocity v. These are points B and A. So the point A on the link will also undergo the same velocity. What can you say about the velocity of the point B on the link? Now, since point B on the link and the center of the disk are pinned together, both will have same velocity, but the center of the disk can only move horizontally, right? Which would be in this direction, let's say, that's VB. So point B of the link will also move horizontally only, correct? So here is really interesting thing here. Can we just from the figure find out what would be the angular velocity of the link? Now link is a rigid body, so it will have both translational and the angular velocity. Maybe can we find out where is the instantaneous center of rotation of the link? So that we can find out geometrically, isn't it? So you simply draw vertical lines from B and A. So here is the vertical line from B and then from A. And that's your IC, instantaneous center of rotation. And then the center of the link could be, let's say, somewhere here, which is C. Okay. So can we now find out what would be the omega of the link? So let me first write down what we have. So velocity of the collar. Okay. So we'll say VCO for collar. And everything is with respect to, let's say, inertial frame. So I'm not going to write explicitly CO/I everywhere. So it's implied. So velocity of the collar, that's negative Vj, isn't it? Now, velocity of the disk center, which is Vb, that's negative Vbi. Now, what can we say about the angular velocity omega of the link? So from the picture, you can see that the sense is such that the omega is clockwise, right? Then only the velocities at A and B will have this direction. So clockwise meaning what? It's going into the paper, so that's minus omega k. So this is minus omega k. But what is omega itself? How do we find out omega? Now this angle, this is theta. So what can we say about this length? The length of the link is L, that is given. Now if this is theta, then that's also theta. So this is nothing but L cos theta. Likewise, this one, that's L sine theta. Right? So from the instantaneous center, whose velocity will be 0. So omega times L cos theta is then simply V. Right? So we have the following equation. Omega times L cos theta is equal to V. So that implies omega is equal to V by L sec theta. Correct? So once omega is known, we can also find out now what is VB. So VB is nothing but omega into L sine theta. So VB is nothing but omega into L sine theta. And omega is V by L sec theta. So this is simply V tan theta. Right? Very simple. So you see, we have found omega in terms of V. We have also found VB in terms of V. What about the velocity of the center of the link, VC? What is VC? Now you see what's the distance? What can we say about this distance, for example? Any idea what will be that distance? Well, that's nothing but L by 2 if you see carefully. Because you see, this is the rectangle and that's the diagonal, and C is exactly halfway on this diagonal. Right? So this green thing, that's the rectangle. And point joining IC and C is halfway on the diagonal. And the diagonal, one of the diagonals is L, which is the link itself. So the other diagonal is also L. So IC to C is simply L by 2. So what is then VC? The velocity of the center of the link. So of course the direction is a bit tricky, but then the magnitude, that's not hard, right? So this magnitude is simply omega, simply omega into L by 2. And omega we have found out V by L sec theta. So this is simply V by 2 cos theta. Okay? So now we have everything in terms of the velocity of the column. So what's the kinetic energy of the system then? So kinetic energy of the system That's Ke of the collar plus Ke of the disk plus Ke of the link. For the collar, it is half mv square. For the disk, it has got translational as well as rotational, right? What is omega of the disk? Since VB, the center of the disk, is moving with VB, so omega is simply VB by R, isn't it? So I can also write that somewhere, that omega of the disk is nothing but VB over R, right? Which is V tan theta divided by R. Alright, so coming back, so kinetic energy of the disk, it has got two parts, translational and rotational kinetic energy. The translational kinetic energy is half into m1 into vb square, which is v square tan square theta, plus half I omega square. You see, this is a planar problem. So it's rotating about an axis which is coming out of the paper, right? Perpendicular to the paper. So about that axis, the I is the polar moment of mass, right? So the IZZ. So what is IZZ for the disk? That's simply mr square by 2. So we have half into mr square by 2, correct? Half I omega square. And omega square, we just saw, it is VB by R whole square. And VB is V tan theta divided by R whole square. Okay, so that's for the disk. Likewise, we have to write it for the link. So for the link, again, it has got translational kinetic energy and rotational kinetic energy. The translational kinetic energy is simply half m2 into velocity of the center of the link, which is Vc, and that's V by 2 cos theta. So we have V squared by 4 cos square theta, right? So that's the translational kinetic energy plus the rotational kinetic energy, which is half into IZZ of the link about its center, which is nothing but ml square by 12, right? So it is m2 l square by 12 into omega square, omega of the link, which is v by l cos theta whole square. Okay, so that's the kinetic energy of the system. Now, what are the forces external to the system? So we have the reaction from the ground on the disk, which is external to the system, but that does no work, right? The vertical reaction, for example, does no work because the point of application is not undergoing any displacement in the vertical direction. What about the horizontal reaction? That's a friction from the ground. But again, because of rolling without slipping, the point of contact has got no velocity. So therefore, the work done by friction is also zero. So as far as the external force from the ground is concerned, they do no work. Then what are the other things? Then we have the gravity. for the link, for the disk, and also for the collar. So that's the conservative force, right? And that can go into the potential. So suppose we choose this as the reference line. The blue line is the reference for potential. So at theta, for a given theta, what is the potential? The disk has got no potential, right? Because the disk is on the reference line. The links has got some potential. The center of the link, C, the C, that's at a distance, you see this distance, above the datum or the reference line. And how much is that distance? That's nothing but L by 2 sine theta. And for the collar, it is at L sine theta. So what is the potential V of the system? We have for the link, which is mass of the link, m2 into g into the distance of the center of the link from the reference line, which is L by 2 sine theta. And remember there are two links, so it has to be multiplied by 2, plus the potential of the collar, which is nothing but m3g into L sine theta. Right? And see, we have also missed 2 above here. So for the disk, there are 2 disks, so we have 2 times this. Likewise, for the link, there are 2 of them, so it is 2 times this. Okay, so we have now written down kinetic energy and potential of the system. Now, what is remaining then is the friction from the vertical bar on the collar. So that's also external. But that friction does some work, right? Because the collar and the bar have got relative motion. So whatever distance the collar goes down, the work done by friction is simply F into that distance, because the friction force is given and it is big F constant. Okay? And it is going to be negative, right? Because friction acts in the direction opposite to the displacement. So what's the displacement of the collar in terms of theta? So for a given theta, the location of the collar, so I can write here the distance traveled by the collar. That's simply the initial position, which is L sine theta with 1, because the initial theta is theta 1, minus L sine theta, correct? So that's nothing but L into sine theta 1 minus sine theta. And notice here theta will be less than theta 1 because the collar is going down, and therefore this number is positive. So that's the distance traveled by the collar. So the work done, the non-conjunctive work done, is simply minus F into L into sine theta 1 minus sine theta. Okay? And now we are ready to apply the work energy principle, isn't it? So it says Ke plus V, let's say at state 2, minus Ke plus V at state 1, which is the initial state, and 2 is the current state. It's initial And that's equal to work done by the non-conjunctive force minus FL into sine theta 1 minus sine theta. And you see, initially it has got no kinetic energy, so this is 0. And it has of course got some potential initially. Right? You simply have to plug in theta equal to theta 1 here for initial potential. Okay, you see the expression of kinetic energy? It is in terms of velocity of the collar, v, and theta. The entire expression is in terms of velocity of the collar and theta. So when we come to this formula here, everything is now in terms of velocity of the collar in the current state and the current theta. So using this equation, we can find out what is the velocity of the collar at any given theta. Okay, so this equation can tell us the velocity of the collar for any prescribed theta. Which is less than theta 1, the initial theta 1, but it has to be of course greater than 0. Can you see this? Why it should be greater than 0? You see, come back to this picture, when theta is equal to 0, it is exactly vertical. Sorry, when theta is equal to 0, the links become horizontal. And when theta goes negative, the collar is going to then compress the spring. Can you see this? And we haven't taken into account a spring here. So when theta becomes less than 0, we have an extra external force from the spring, which is also going to do some work. Right? So this expression therefore only holds when theta is greater than 0. Can we, for example, find out what will be the theta to which the collar will go down before coming to rest? So at what theta the collar comes to rest? So you see, look at the system again. So this is the initial state. You leave it at this state. The collar starts going down. It picks up velocity, although there is friction acting. But the gravitational force or the gravitational pull is more than what's the friction there. So the collar goes down. Its velocity keeps on increasing. Then we have theta equal to 0. It gets in touch with the bottom spring, and the collar will further keep on going down, and that's when the spring starts to exert force on the collar, and it's going to then decelerate the collar, and there will be a final theta at which the collar will then come to rest. So can we find out what will be that theta? So that's also quite simple. So we have to look for a negative value of theta at which the collar has come to rest. And remember, the omega of the link, the velocity of the center of the link, the velocity of the disk, the omega of the disk, they are all proportional to velocity of the collar. So if the collar comes to rest, everything else comes to rest. So we want to look for a final state when everything has come to rest. Okay? So in that final state, suppose the angle is some theta, but the negative theta, how much will be the work done by the spring on the system? So work done by the spring is simply half kx square, right? Where x is the compression of the spring. So the final work done, so we are looking for negative value of theta, right? It is going to come to rest for negative value of theta when the spring also starts to exert force. Okay, so the final state is going to be something like this. So we have the disc, and here is the spring, here is the collar, and then the two links, right? Let's make the collar bigger. And here is the angle theta. See, this problem is easier because there is no kinetic energy involved in the initial state and the final state. So it's just the question of computing the potential. So the potential, we already know the initial potential, V1, when theta was equal to theta 1. What was that equal to? So we had 2 times m2g L by 2 sine theta 1 plus m3g L sine theta 1. Okay, and the final for this negative theta, the V2, that's nothing but two times m2g L by 2 sine theta with a minus sign, right? You see, because it is going below the datum, minus m3g L sine theta. So when we come to the work energy principle, the work done by the non-conservative force in going from 1 to 2 plus the work done by the conservative force in going from 1 to 2 is equal to delta K in going from 1 to 2 plus delta V in going from 1 to 2. Okay, now this is 0. The delta V in going from 1 to 2 is simply V2 minus V1, right? And you see this potential here does not contain the potential of a spring. It's very interesting because initially when you formulated the potential, the only conservative force which was acting on the system was just the gravitational force. But now we also have a spring force, but we did not take a spring as part of the system. The spring is external to the system, and therefore it's coming here on the left hand side. So this is the spring work. And you see the force exerted by the spring on the collar, it's always upward, but the collar is going downward. So work done by the spring is the negative, isn't it? and that's nothing but minus half into spring constant K into compression of the spring whole square, and the compression of the spring is L by 2 sine theta whole square. Okay, and finally the work done by the non-conservative force, that's simply minus F into the distance traveled by the collar, which is L sine theta 1 plus L sine theta. See, it comes with a plus sign because it has gone on the negative side, right? The final displacement, final position of the collar is below the datum. So we get a plus here. Okay, so you solve this problem. Theta 1 is known, the unknown is theta here, and then you can find out what is the final theta for which the system again comes to rest. Okay, quite easy, right? Similarly, if you had to find out, as I told you in the beginning, what will be the acceleration of the collar when the system is left initially. So for that, we have to use simply the rate form of work energy principle, which is this, the rate form. Or what you could simply do is simply, okay, I don't see it here. Basically, you see, you have the expression for the kinetic energy of the system. For any theta, you put it in this equation right here and take the time derivative. Take the dot and you'll get k dot. And likewise, you have w dot and w dot nc. Okay, so I think you can find it now. So when you do k dot, for example, so let's try to work this out for maybe. So we want to use the rate form. So that's w dot by the conservative force plus w dot by non-conservative force, that's equal to k dot. Or we could also write this as w dot by non-conservative force is equal to k dot plus v dot, right? Where v is the potential of conservative force. So we have the expression for kinetic energy, we have the expression for potential also. Look here. So that's the expression for potential. This is equation 2 and that's equation 1, the expression for kinetic energy. So we simply put it here. This is equation 1 and this is equation 2, and take the time derivative. Okay. Similarly, we also have the expression for work done by the non-conservative force. You see, that's equation 3. So this is equation 3. So let's, for example, do w dot nc, and what we will get. So WNC, we already have the expression. That's minus of F into L sine theta 1 minus L sine theta. So W dot NC is simply minus of F into, see, theta 1 is a constant, so this is not going to come. into minus L into cos theta into theta dot is equal to F into L into cos theta into theta dot. And what is theta dot? Just look at this formula here, or look at this picture. What is theta dot? So theta dot is nothing but omega of the link, right? So you see theta defines the orientation of the link. So theta dot is simply omega of the link, and we had found out omega of the link. So here is the omega of the link. The omega is V by L sec theta, or V by L cos theta. So we can put it here. So this is F into L into cos theta into V by L cos theta, right? So these cancels, and finally we have F into V. Okay, I think we are missing a minus sign somewhere, so you can figure it out. Why I say we are missing a minus sign? Because you can also get directly the power of the non-conductive force. The non-conductive force here is nothing but the friction, and the velocity of the collar is V. So friction is acting on the collar, so the power by that friction is simply minus of force F into velocity of the collar going down, right? So therefore I said we are missing a minus sign, so you can figure out. So W dot NC is simply minus of F into V. Okay, but for the other things, K dot, so you have the expression for K, you take the dot. So V square, for example, when you take the dot, you get 2V into V dot. Similarly, you have theta. So you take the dot, you get theta dot. But theta dot is known in terms of V. So finally, when you do the K dot, you'll get an expression in terms of V, theta, and V dot. Okay, so this expression here, K dot, this will be in terms of V, theta, theta dot, and V dot. But theta dot itself is a function of V and theta, right? The omega. So this is finally a function of V, theta, and V dot. So K dot will be in terms of current velocity of the collar, theta of the link, and acceleration of the collar. So you can see that this equation will finally be in terms of the unknown V dot. And at the initial instant, the velocity of the collar is 0 and theta is equal to theta 1. So in this expression, you simply plug in V equal to 0, theta equal to theta 1, and you will just have V dot remaining. So you solve that and get your V dot, or the acceleration of the collar when the system is just left. Okay, so this completes this problem. Okay, let's now do some example for calculating the work done by a force along a path. So let's think of a force having the following form. So you can see the basis vectors are in cylindrical coordinate system, and here is the path. So the path is basically circular. All right. And its diameter is d. So it goes from the point A here to the topmost point G over here. Okay, so this is the path. So the work done, naturally, we know W is integration along the path F dot dr, correct? So what will be r in the cylindrical coordinate system? So that's nothing but small r er, and dr is then dr er plus r d phi e phi, right? So we can simply plug this in the formula over here, and so we have integration c over r cube er plus b e phi dot with dr er plus r d phi e phi, okay, which is simply c over r cube dr plus b r d phi, isn't it? And we have to go from A to G. You can see here the 2 points. This is point G and this is point A. So as you can see, this integral has decomposed into 2 parts. The first one is only r dependent, where the second one is just the angle phi dependent. So working out an integral is not difficult in this case. So we simply have to find out what is the initial r here and the final r. So initial is of course d, and the final, you can see from this figure. So this becomes the right triangle. This is d by 2, this is also d by 2. So this green line is simply d by root 2. Okay? And the angle, then how much is this angle? This angle, since this is a right angle triangle, so this is simply pi by 4, isn't it? So basically, this integration then becomes, the first one goes from d to d by root 2, because we have to think of how r is changing, and then this is c by r cube dr, and the second one is then plus b r d phi, and here it has to go from 0 to pi by 4. If you work this out, so c r to the power minus 3 dr. So this becomes c over minus 2 into 1 by r square. And the integration goes from d to d by root 2. The second one is tricky. You see, integration is an angle B R D phi, and we also have R sitting here. So we have to know how this small r is changing as phi changes. Okay, so if we come back to the picture, for any arbitrary angle phi, this is phi, then what is this r, small r? Alright, so you can see, since this is a circle, this is going to be a right triangle, and that means this small r is then simply d into cos phi, isn't it? So we can come back and substitute small r as d cos phi. So this is finally minus c by 2 into 2 over d square minus 1 over d square plus bd, and cos phi d phi becomes sin phi, and this goes from 0 to pi by 4. Okay, which is finally minus c over 2d square plus bd sin pi by 4, which is 1 by root 2, so this is plus b over d by root 2. Okay, so this is how we calculate the work done along the path. What's crucial here is that in the second integral here, the small r has to be replaced in terms of phi, because the variable of integration is phi over here. Alright, let's do another example. So again, a very simple example, but the trick is how to do the line integration accurately. So suppose the force field F is x, y, z, I plus y square j plus z square k. Okay, and we have to integrate along the following path. So the final point is 1, 1, 1, and the initial point is 0, 0, 0, and we have to go along a straight line. Alright, so as per the definition, W is simply integration along the path of F dot dr. Okay, and what is r in this case? So here we are using Cartesian coordinate system. So position vector r is simply xi plus yj plus zk, or dr is then dxi plus dyj plus dzk. Now if I think of working out the integral, this is simply f dot dr, which is then xyz dx plus y square dy plus z square dz. Okay, now what should be the limits of the integration, for example? So the second integration over here, it has y square dy. So you can see the variable of integration is y. So we have to think of what is the lower limit and upper limit of y. So here, for example, it goes from 0 to 1. Similarly, last one goes from 0 to 1. The first one is again, the variable of integration is x, which is also going from 0 to 1. But the tricky thing is, this integrand has also got y and z. So we have to think of how to write y and z in terms of x along this path, along the given path. So you see, because this path is a straight line joining 0, 0, 0 and 1, 1, 1, any point on this path is such that x comma y comma z has the following form: x comma x comma x. So basically y is equal to x and z is also equal to x. So that means we can come back here and write down y and z both in terms of x. And this is then 0 to 1 x cubed dx plus 0 to 1 y squared dy plus 0 to 1 z squared dz, which is finally, the first one is simply x to the power 4 by 4, so it's 1 by 4. The second one is y to the power 3 by 3, so it is 1 by 3. And the last one is also 1 by 3. And this is finally by 12, 3 plus 4 plus 4, 11 by 12. So that's the work done. Okay. Another way to do this line integral is by parameterizing the curve. So look at this curve, which is a straight line, of course. So can we parameterize this using one single variable? So a straight line, for example, what is the formula for a straight line which starts from point A and goes to point B? So let me do this calculation sidewise. Think of a straight line starting from A and going to B, and the direction is T. Okay. So any point small r on this path can be written as small r equal to A plus some scalar, let's say alpha, into t. And this t can also be b minus a, isn't it? So you could also write this as a plus b minus a into t, sorry, into alpha. Okay, so alpha is the parameterization of the curve. So by changing alpha from 0 to 1, we actually trace the straight line. So for our case, a is equal to 0, 0, 0 and b is equal to 1, 1, 1, right? So that means r is simply 1, 1, 1 into alpha, isn't it? So we could write this as alpha into 1, 1, 1. That's your parameterization of the curve. So what is then dr? Dr is then simply d alpha into 1, 1, 1. Also, based on this parameterization, it tells us that x is equal to y is equal to z is equal to alpha, isn't it? So if we go back to our definition for work done, which is simply f dot dr. So in this case, we can write everything in terms of alpha. So f, as per the formula, you can see it is x, y, z I plus y squared j plus z squared k. So x, y, z all are alpha along this line. So it becomes alpha cube I plus alpha squared j plus alpha squared k. Okay. And then we dot with d alpha, which is 1, 1, 1 d alpha. And then you see this variable, the variable of integration here is now alpha, which has to go from 0 to 1. And this is finally going from 0 to 1, alpha cube plus alpha square d alpha, right? And this gives us back the same thing that we had earlier. So it is alpha to the power 4 by 4 plus 2 times alpha to the power 3 by 3, and the limit going from 0 to 1, which is simply 1 by 4 plus 2 by 3, and that's 11 by 12 finally. Okay, so we get the same result as earlier. But what we learned here is that while doing the integration along the path, we have to think of parameterizing the path in terms of a single variable. For in case of a straight line, for example, we parameterized it using alpha. So even for any other curve, usually in the exam, you will be given a curve which can be parameterized analytically. So you have to think of parameterizing it, and you have to then write x, y, z, all three of them in terms of the parameterization variable of the curve. And then the integration along the path simply becomes integration in that parameterization variable. Okay? So I hope you've got some idea about how to do line integration. So with this, I'm going to stop the class today. And in the next class, we are going to learn about collision. All right, thank you.